so I guess I can just get going now that things are, ready for the science bit. I'm kind of pleased by the temperature. I'm a Canadian, and for me, cold is really the source of all interest. I remember at some point when I was a PhD student, an interesting conversation in a restaurant in LA with an experimentalist called Gil Lonzerich, who's doing like experiments in condensed matter. I don't know if any of you know him. He's an older generation. And he said, I don't know, why people find it so bad about the death heat of the universe and whatnot, because all the interesting physics occurs at cold temperatures. So I think maybe you're kind of feeling that in the audience here. So for me, yeah, it's Canadian weather. I'm thinking if we're doing courses at 9 Celsius or whatever, maybe we should start a school in Canada at -30 and see how far we can get. But anyway, so I'll try to warm things up for you a bit this morning. Yeah. Thanks a lot for the invitation to give these lectures. So it's always a good opportunity to try to maybe instigate a bit of integrability in the young generation. That's what I'll try to do in these 3 sessions. Honestly, 4.5 hours to present what I intend to present you is completely bonkers. So I warn you, the pace is going to be absolutely insane, okay? But I am experimenting with a slightly different way of teaching here. It's essentially not really a course like a traditional course. It's more a kind of orientation guide onto the field. I will give you pointers to the resources that you need to fill in the blanks, okay? So I'll give you more detail. You'll see how it goes. The course is divided into 3 parts. First part is really kind of methods, getting to know the language, the methods and things. The second session is going to be about the use of these methods in equilibrium physics, just to kind of consolidate your understanding of this. And only in the third part will I really go out of equilibrium. And then I will essentially batter you with results on these things and ideas for future things. Hopefully you'll walk out of here with a complete, whirlwind of a headache. But hopefully this will serve your further purposes as, as time goes by and your career does. So my name is Jean-Sebastien Caux. I was essentially asked this morning how I should be called. If you're Dutch, you can call me whatever you want because that's what Dutch people do anyway. But you can just call me JS. You can also call me Tintin, all very appropriate in France. And whatever, just inform me how you call me so I can recognize it, and then we'll all be happy. During the course, please interrupt me at any moment if you have like important questions or interrogations, because if I don't get interrupted, then I accelerate the pace. So if you want to keep me from going completely wild, then it's good to ask questions. Okay. So to get things going, I just give you some indications of what's coming in sessions 2 and 3. In session 2, like I said, in equilibrium, I'm going to talk about dynamical properties of integrable systems. I'm going to talk about experimental correspondence. I'm going to map also with the course you're going to get on Luttinger liquids, because I'll have things to say about field theory. And then the third session, we're really going to go out of equilibrium. I'll talk about quantum quenches. I'm going to talk about an approach that's been used quite a lot recently called generalized hydrodynamics. And I'll talk about some dreams of stuff that I'm not yet able to do except in specific circumstances having to do with driven systems. But before we kind of get going here, I want to maybe try to justify why we do this kind of thing and why I'm particularly interested in this kind of field. So there are some big questions around that you might have heard about. So what does integrability really mean? The meaning of the word is really not completely agreed. Classically, in classical mechanics, everybody knows what that really means, but in the quantum case, that's not the case. One of the accusations that's often given to people who work in integrability is that these systems are not normal. They're exceptional. They're like points in the possible space of all models that have no physical interest because, they don't correspond to real things in the lab. So it's a thing I personally strongly object to, but I'll try to include you in that debate a little bit. So these models are the exception rather than the rule. Can you essentially use any of this beautiful mathematical technology to do anything useful in more traditional settings? Well, it's essentially difficult to perform any calculations with these models due to the really technical difficulties associated to that. So there's been historically big blocks on this for decades and only very slow progress in some measure. And then, of course, the question is that since everybody these days is interested in out of equilibrium, can we put integrability as one of the ingredients of this thing? In a sense, once again, here we face this wall of complexity. Wave functions are incredibly complicated. You can't do anything with these things, but sometimes you can. Okay, so I'll try to give you some examples for this. Now, again, at a more kind of meta level, I think for me there are very important things associated to the reasons why I choose to work in this field. And you know, sometimes these reasons always, they can get a little bit personal. So in my past history, when I was young, when I was like, you know, energetic and whatever, I was a PhD student in Oxford, and then I became a fellow in a college in Oxford, which you probably don't know. It's called All Souls College. And this is the ideal academic tower of them all, because the whole institution, it's itself a kind of independent university, it's only made of fellows. There are no students. So everybody there is paid to wine and dine and think about academia. And one of its most famous fellows historically is this chap here, Isaiah Berlin. I don't know if any of you know that name. No? Well, you see, so there's stuff to learn. So he was a kind of philosopher dealing with politics, literature, mixtures of things. He had a very famous correspondence with Anna Akhmatova, who some of you certainly know. Anyway, very, very interesting chap. So he viewed himself as the greatest conversationalist in Oxford. So if you sat next to this chap, you really had interesting conversations. He wrote a number of really, really nice books and essays about certain things. And one of the most popular ones that he wrote is based on an old saying of a Greek poet called Archilochus that says, "The fox knows many things, but the hedgehog knows one big thing." And what's the interpretation of this when you're a physicist? Well, all of you have faced courses in quantum field theory and kind of general approaches to generic models. Perturbation theory, you just write a generic thing, and then you learn these methods that are always applicable. On the other hand, you know, some of us have learned things like, you know, a beta ansatz. Yeah, so if you're the fox, that's what you do, right? So you know how to write Hamiltonians, you know how to write partition functions, you know how to write perturbation expansions, Fermi's golden rule, path integrals, diagrammatics, etc., etc. And these days, you know, you just add numerics to that because you can throw any theory onto these things and hope to get something. On the other hand, the poor hedgehog here knows how to do one thing, which is to write a beta ansatz wave function, which you will also know how to do at the end of this hour. It's the one thing that this hedgehog can do. But essentially, if I interpret the history of integrable models over the last few decades, well, it goes as follows. So the hedgehog first realized that there were extremely profound and beautiful mathematical structures at the base of all the technology associated to integrable models. There was a like theory of everything on these things. There was a really kind of an abstraction layer created for these things where suddenly a unified theory of integrable models appeared. That's called the algebraic beta ansatz. And with this technology, suddenly some practical things became possible. One was able to compute essentially things that started looking dangerously like things you need to do physical computations. Norms of states, effects of matrix elements of operators in the basis of these exact eigenstates. And then you could start cooking these things up in ways that really addressed some things. For example, response functions of models, how systems react when they are probed in a certain way, and how their dynamical response looks, so at finite frequency, at finite momentum. And this thing allows to make direct correspondence to physical experiments on systems whose Hamiltonians are approximated by integrable models. So that's the statement. Over the last, call it 20 years, the hedgehog of integrability has, for me, transmogrified into the fox of integrability, because now you're able to make very, very hard statements about these things that were previously inaccessible. The price you pay is that you can't do it for every model that's around, but for the models for which this works, this surpasses all other available methods and becomes a kind of benchmark for all the other methods. So I'll try to give you examples of this and motivations to look further in that thing. Okay, so that's the kind of grand scheme of things for this. Now, I guess many of you already know a bit why 1D is special, why these things are interesting. I mean, I guess, how many of you work in like low-dimensional or even one-dimensional systems? Yeah. Preaching to the crowd, yeah? Okay, very good. So why is 1D special? Well, just as a quick summary, because of the constraints, of the geometrical constraints of that system, that means that whatever interaction you put in there, if it is a function of distance, then it will probe its very highest achievable effects in 1D because particles cannot avoid each other. Okay? So anything perturbative fails. Fermi-liquid theory, all these ideas, you've got divergence susceptibilities, you can't resum these things, Fermi-liquid jams up in 1D, you can't do that. So what can be done? Then, of course, if you're old school diagrammatics, then you do parquet approximations like Tsioloshinsky-Larkin. You sum all these things up, and you realize, yeah, indeed, anomalous power laws in response functions and things like that. If you're somebody like Duncan Haldane, building up on a whole history of people working in these effective things, you realize that there's a profound meaning to that. There's a new universality class in 1D. It's called the Luttinger liquid, where things essentially are very non-Fermi liquid-like. Once again, these strange power laws show up. But you can really write a framework that's valid at low energies on these that allows you to capture all these effects. Okay, so Duncan Haldane's Luttinger liquid here. Of course, you can also do numerics, but for me, what's the kind of sexy thing about this whole thing is that you can really afford to say, you know what? I don't want to compromise. I'm going to write a Schrödinger equation, and I want to see the exact wave function. And I want to see how that looks, and I want to see how that behaves. So you try to use these exact methods based on integrability, starting from Beta 1931. I'll introduce you a little bit to the history of that. But that's going to be our focus throughout these lectures. Okay, so all these words, yeah? So why would you want to study that? Once again, like I said, these models are the exception rather than the rule. You might have a feeling that theory developments take geological timescales. We can trace the history of integrable models really directly back to 1928. But sometimes you have to wait decades for new things. There's a no easy way out kind of business. But for me, it's really crucially important that once you make statements based on these things, then you rely or you stand only on the postulates of quantum mechanics. So if you still believe in quantum mechanics, you are essentially drawing conclusions directly from that. And by extension, for me, this is the hope of also perhaps finding strange things in quantum mechanics, challenging it to higher levels. It's really to push its predictions further than other methods here. So that's one of the motivations here. And of course, on the side, I don't think I would be here today if it hadn't been that my scientific career had been saved by the fact that some of my calculations had experimental correspondence. Okay, because it's much easier to draw interest of people if indeed your calculations map to certain things that are measured in the lab. I'll show you some examples of that. But I view this as a kind of fuel to the whole thing. It's not necessarily the primary motivation for all that I do. And again, so for other people who do like numerical methods and things like that, a kind of nice side effect is to provide these beacons that I talked about for testing other methods that themselves might be more generally applicable to this. Okay, so that's kind of context. Is that cool with everybody? Yeah, okay, good. Now, where do we start? So what I'm going to do here, I'm going to give you a few slides to give you just a very broad overview, kind of key concepts that we're going to use and we're going to build upon later today. So Hans Bethe, essentially, I was joking this morning. I was asked, how I ended up here. When I was young, I was wanting to be an astrophysicist. I was interested in energy production in stars. Therefore, I had read the reviews from the 1930s from Hans Bethe about nuclear physics. So he's the one who figured out the carbon cycles, CNO cycles in stars and whatnot. But on the side, he had published an isolated paper in 1931 when he was visiting Fermi in Rome. So he was himself, of course, of German origin. And I'll show you a little bit of the history of that. It starts in 1931. So what's the idea of a model that we call beta-ansatz solvable these days? Well, you've got a Hamiltonian, which is really an energy density integrated over a one-dimensional line. Okay, so the Hamiltonian itself has contributions from local aspects of the physics. And you start from a state that is obviously an eigenstate. For example, if you've got interacting atoms, the state without any atoms. Okay? And on that reference state, you will build eigenstates by adding particles. For example, you will add atoms one by one. And the wave function that you will get essentially takes a form which is universal to all beta-ansatz solvable models. It's written a little bit like a beast here, but you can view it as a slightly nonlinear generalization of a Fourier transform. It's just a Fourier transform with some little dressings. So what is it? An n-body wave function is just a product of n plane waves. When the particles are separated from each other, they have a plane wave. When the particles collide, they have a scattering phase shift. We'll discuss this a little bit more in a few minutes. The scattering phase shift essentially represents the interactions between pairs of particles and how the wave function of the particles changes when the particles cross each other. These things here are just phases. They don't reorganize the momenta. But these phases are so chosen that you solve the Schrödinger equation for these two colliding particles. On top of that, you've got a parametrization in there in terms of internal quasi-momenta. So they're not really momenta in the sense of, translational invariance in your system. They're like quantum numbers, quantum labels that you have. But internally, when the particles are free, they do look like what you would call momentum. That's the labels that we use for the wave functions. Very importantly, there's a kind of fermionic character to all these integrable models, even if it's a model of bosons with interactions. There's a fermionic character in the form of a Pauli principle, namely that any given available slot for your quantum number can be occupied once or not occupied. No further choices. That means that you can build a catalog for all the eigenstates in your Hilbert space by simply choosing all possible sets of allowable quantum numbers. We'll do that in a little bit more detail later, just giving you a kind of orientation for this. Okay, so that's the general idea. Now, again, as a kind of historical context here, so we're going back to 1928, when life in physics was very much easier than it is today, because every single paper that was published in those days had the same title, Zur Theorie des Ferromagnetismus, okay? And I'm literally not joking. I mean, not all papers, but you'll find many, many papers. Don't search for a paper by its title. You won't find it. So 1928, people wonder why pieces of matter display magnetization, measurable macroscopic magnetization. Doesn't make sense. Atomic theory does not predict that. Many-body physics of the day and age is very much in its infancy. You're really kind of a year and a half after the birth of quantum mechanics here. So people don't understand. So people write effective models to understand this. And the most famous model, of course, is Heisenberg's model of spin-half operators coupled to their nearest neighbors on a one-dimensional chain. So that appears in that paper. And then, you see, this is proof. There's a great missed opportunity from Felix Bloch. I guess it's just that he was in Utrecht at the time, and so I guess they just didn't want complexity and things. Felix Bloch made an approach to try to provide eigenfunctions of this Heisenberg chain. But he oversimplifies some aspects of the calculation. At one point, he encounters a logarithm. He needs to take a kind of expression. There's an arctangent in there, complicated phase. He says, don't like logarithms, don't like arctangents. I just put the phase to 0 and therefore greatly simplify my thing. And, of course, misses out on eternal fame because he gets wrong states. That means he doesn't get even the number of states correctly, and he forever misses on the opportunity of having the Bloch ansatz known for him. Okay, so that's it. That's the lesson here. If you encounter a little bit of complexity in your calculation, don't be too quick to throw it out, because you might make a big mistake. Now, Hans Bethe really kind of displays great creativity here, first of all, by the choice of title of his paper, Zur Theorie der Metalle. Okay, so it's kind of funny because it's got nothing to do with metals. Yeah? So it's really about magnetism. Now, he proposes a correction to the calculations of Bloch, where he indeed takes care of branch cuts and logarithms in the complex plane and whatnot, and carefully computes the eigenstates of this linear chain, this Heisenberg model, carefully counts the number of eigenstates, and really obtains the absolutely exact number as expected from the basic principles of representation theory of tensor products of n spin-half operators, etc. Already fully developed at the time, actually, very impressive. So June 1931. And yeah, that's the main thing here. And what's really funny about this, this paper is that you kind of see the level of confidence that Bethe had, because it's paper number 1, okay? And it's paper number 1 of a series of papers that is announced here, where Hans Bethe pre-announces the generalization of this method here to higher dimensional crystal lattices. Of course, that's complete bullshit here. It is, I think, the only phrase in the published corpus of Hans Bethe where manifestly he is caught with his pants completely down, just bullshitting away to that level. He hadn't even tried the calculation, because had he tried even 5 minutes, he would have realized that it doesn't work, because the permutation group in 1D has very different representation theory than in higher dimension. It just doesn't work here. But anyway, so that was paper number 1. That was the announcement here. Never came about. Yeah, that's the only paper Bethe ever published on Bethe ansatz solvable models. In fact, he was asked many years later by a Russian famous person in the field how it felt to be the father of the Bethe ansatz, and he answered, "The Bethe what?" So he had no clue what this was about. Yeah? Completely disconnected from this. Okay, yeah. So that's the kind of context. So another funny anecdote about Bethe is that I'm getting on a bit. In early 1994, I was looking for a place for a PhD, and so I had offers from various places, and one of the places was Cornell University in the U.S. And Hans Bethe was in Cornell, and he was still working at that time. Hans Bethe died in 2005. So I visited Cornell, and because I didn't know better, I had learned a bit of Bethe ansatz back then, so I went to knock on Bethe's door. And so I remember he was sitting at his office, and then he put his hearing aid on very slowly, and he said, "Come in, come in." So, and I had a chat with him. So he explained to me back then what he was working on, which was the theory of neutrino oscillations. It is said of Bethe that he's the only researcher in the history of physics that for 8 consecutive decades produced work in different fields, each worthy of a Nobel Prize. He's the only one who did that, way above the accomplishments of even people like Feynman and things like that, way above. So in that particular decade, he was working on neutrino oscillations. So he explained to me a bit all his theories of neutrino oscillations and whatnot. And then before I left, I asked him the fateful question, so if you had one thing to recommend to a young theorist who wants to do well, what would it be? And you have to realize that Bethe was in the US since 1935, but he still had a very strong, deep German accent when he spoke. So when I asked him for this one tip, I was really hoping he'd get this manuscript out of his drawer, and say, "Oh, just finish that thing, and then, you'll be done, you'll be made. It's going to be fun." But he just said, "You have to work very, very hard." So I was a bit disappointed, but in the end, that turned out to be a correct prediction, actually. So I'll pass this recommendation on to you as well. Okay, so that's the context. Now, what you will see is that I'm going to give you the recipes to construct eigenfunctions of two representative models of the class of integrable models. We'll quantize these things. You'll see these so-called beta equations appearing. Get more details about that. Show you how to classify states with these quantum numbers, how to construct a basis of states for these things. Again, just like pre-announcing this in 2 minutes. I'm going to show you how to navigate the Hilbert space by indeed just tuning these quantum numbers to chosen configurations representing fundamental excitations in these systems, how you can understand these things physically, how you can map them to observable quantities in here. We're going to talk about a number of models, but the two that I'll already mention here are the Heisenberg spin half chain, the one that Bethe solved in 1931. It's got a generalization by a person here. That's one of the really funny things in the field of integrability, because the XXZ model is certainly the most used model in the field of integrability. However, nobody in the field of integrability knows who actually did this diagonalization here in 1957. This chap's name is Ray Orbach, and in the good tradition of Hans Bethe, he only ever published one paper in the field of integrable models, but his name is kind of unknown, so I'm trying to revive his glory on this. Okay, so there's also other generalizations. Rodney Baxter's 8-vertex model, XYZ chain. Not going to jump on this. They're also much more complicated. I'm just showing you a variety of models here that essentially succumb to the technology of integrability. So the wave functions of all these models for, again, interacting spins with more complicated representations, models for interacting fermions, models for discrete systems, touching on nuclear theory and whatnot, other magnetic systems like this, impurity models, Anderson models, and finally, the one that I'll start with in my later considerations, the simplest integrable model out there, which is a model for interacting bosons in one dimension, so-called Lieb-Liniger model. I should have put a picture of Werner Liniger here. I have it somewhere. Ah, there he is. There he is. Yeah, and the joke behind this is that, the Lieb-Liniger model, so that was solved in 1963. I did not have a picture of Werner Liniger, so I contacted Elliot Lieb, the gentleman on the left, to ask him if he had a picture of Werner Liniger. And the answer was, not only do I not have a picture of Werner Liniger, I don't even remember what he looked like. So it was quite brutal. But again, in the great tradition, Werner Liniger published this one thing and then disappeared from the field. Sadly, this is a picture from his obituary a few years ago, actually. But anyway, so life is tough in integrability. Okay, so that's the kind of contextual introduction to the whole thing. And good moment for questions, because now what I want to plunge into for the rest of this morning's session is learning the skills, so actually writing equations and getting things. Are we all cool? Everybody a bit warmer already, or is it still cold? Or yeah, still cold. Okay. So what I'm going to do here is, I wasn't quite sure what kind of blackboard I'd have. I have a lot of things that I want to present. So we're going to go a bit experimental here. We're going to actually go to a website in which I have published lecture notes on integrability. Okay? And it's kind of easy to remember, integrability.org. And I will come back to the presentation mode when we carry on tomorrow. Okay, so what are we going to do here? Integrability.org is just this website. Maybe I can increase the magnification a bit. Something like this, a bit more legible. Okay, so on integrability.org, you'll find the current version, I'm not saying it's complete, but of a complete set of lecture notes for learning the basics of integrability. Okay? And I'm going to show you how to navigate that thing. So first of all, there's always a table of contents that you can look at that contains all the sections, subsections, and whatnot, so navigation is quite easy. So if you're, if you're on the bus, on your phone, or whatever, you can just like check a few more equations with these things, and we see how it goes. So instead of writing all the equations on the board, what I'm going to do is I'm going to use the equations here and give you perhaps needed complements for you to understand the equations here. But in the hope that you will later just be able to refer to this and come back to this and keep your bookmarks on these things. Okay, so just an experimental way of doing it. I'm not sure it's going to work, but we'll give it a try. Certainly in view of the time that I have here, that should work. I gave a course in Padova earlier this year on integrability. I had 48 hours of lecturing to do the material. I'm kind of trying to do maybe half of it in these 4.5 hours. Okay, so we'll see how it goes. Okay, so here goes. Now, when you think of the theory of integrability, I would invite you to classify this into 5 subdivisions. The first subdivision is really historically the first one to appear. Actually, they're kind of all historically ordered here. It's the so-called coordinate beta ansatz. The coordinate beta ansatz essentially is writing down wave functions in real space that solve the Schrödinger equation of Hamiltonians, solvable by beta ansatz. So this is what beta initiated in 1931, and I'll show you 2 examples of how this works. Now, a few decades pass. Between 1931 and like 1963 and 1968, nothing happens except for one isolated paper in 1938 where Hultain computes the ground state energy of the Heisenberg antiferromagnet, and 1957 when Ray Orbach solves the XXZ model. But then suddenly people start being more fancy. So people like Xian Yang, then in the US, started looking at the thermodynamics of these models, namely how you can compute partition functions for these exactly solvable models, how you can compute equilibrium properties of these models using really beautiful functional integral methods obtained when taking the thermodynamic limits. I will go very briefly on this because we're not going to use much of that technology here, but you'll find it exposed in these lecture notes. Then in the late 70s, beginning of the 80s, there appears from the school in Russia under Ludwig Fadeev, there appears this realization of these beautiful mathematical structures at the base of all these quantum integrable models. And this whole field is now known as the algebraic beta ansatz. I will try to give you a bit of an understanding of where this comes from. But again, we'll refer to the lecture notes for more details. Then starts the cooking part, because all these ingredients here can be put together to try to make contact with experiments. So when I was a PhD student and young postdoc in Oxford, I had a good friend who was a neutron scatterer. So we were sitting here at that point. And this good friend of mine, Alan Tennant, was saying, JS, yeah, I see the beautiful equations. They're like really attractive, really, nice looking and very impressive and whatnot. But, I measure cross sections and things. So what's the number that comes out? What's the number, right? And I couldn't tell him a number. And then he was saying, well, what's the point of that then? Yeah? So I said, Alan, okay, I will give you numbers. So it took me a few years, but indeed, at some point, using either some analytical methods or some numerical shortcuts to try to get some approximation to the number, it became possible to cook up all this machinery to start making quantitative predictions for experiments on these things. And these quantitative results I will present to you tomorrow. Okay? But they will use, in order to understand where they come from, you need knowledge of these first 3 sections here. And then later, there was really a realization that with these models, you could approach truly out of equilibrium things. So in the last part of the course, I will introduce you to these ideas here. My objective is going to be to give you an indication of what it's based on, where it's going, what's been achieved, and what can possibly still occur on all of this. But we'll get back to this later. Okay, so at first I really want to do basic technology with you. Okay, but just bear in mind all these different sections here kind of build up to where this is all going. Okay. So let's go concrete then. What I would like to do is start with a specific example of an exactly solvable model. And what we're going to do is consider not historically the first one to be solved, but the one that I consider to be the simplest model to be solvable by beta ansatz, namely the Lieb-Liniger model that I've already flashed in the slides earlier. So what's the model? We are in one dimension. We're, of course, quantum. We have canonical commutation relations for particle creation annihilation operators. There's no ultraviolet cutoff here, so it's really a true continuum. And the Hamiltonian is simply the Hamiltonian of free particles, so energy p squared over 2m, but of course we put, m is equal to 1/2 and h bar squared, h bar is equal to 1. So this is just like the kinetic term. And there's a contact interaction which is counted when particle positions coincide pairwise. The interaction parameter c is, in order for the model to be Hermitian, a real number. However, of course, the wave function itself would work even if c was complex. Okay? This interaction parameter characterizes the nature of the model. If c is equal to 0, of course, you've just got free bosons. If c goes to infinity, you have particles that essentially are such that when they cross, the wave function is 0. So that's like fermions. However, these are bosons. Okay? So in the case of fermions, if I was to keep n minus 1 of the particle coordinates fixed and just have the other coordinate here changing, there would be a node and a change of sign to the wave function here, because the wave function is antisymmetric. Here, because we're bosons, the wave function has like a pinch at c is equal to infinity. So the wave function of bosons at c is equal to infinity is the absolute value of the fermionic wave function. Okay, so that's known as the Tonks-Girardot limit. It was done before the beta ansatz for all these things. But the model interpolates between bosons that are inherently free and bosons that behave like fermions. So it's a really kind of a good laboratory to investigate the effects of interactions in one dimension. Okay, so that's our Hamiltonian. Now, in order to solve this Hamiltonian, it's relatively straightforward. So let's just jump straight to the thing now that you've seen the Hamiltonian. We can look at solving the Schrödinger equation. And I will briefly flash the solution for two particles because it shows the structure for the general n-particle case. What do we have for two particles? We have like a problem of a single particle with an impurity somewhere. So two particles, let one of the particles be the impurity. So it's like solving the Schrödinger equation, like in the book of Cohen-Tanuji, where you've got a delta function impurity at x is equal to 0. You remember how that goes, I hope. Who here was educated with the book of Cohen-Tanuji, Dieu, and Lalleux, and did, very good, yeah, the Argentinian contingent here is like strong. Okay, so what occurs? Well, the wave function itself has a cusp in its derivative at the position of this delta function. So in order to find that, you just need to integrate this equation here in the relative coordinates. And what you find is that the presence of this delta function interaction induces a discontinuity in the first derivative of the wave function at the position of this impurity. And the size of this discontinuity is given, of course, by this parameter, this interaction parameter. Okay? So it's just a kind of matching condition for the wave function's derivative at the positions where particle coordinates coincide. And that's it. And when you look at such a such a condition here? Well, you already know that away from the coinciding positions, this term you can neglect, and now your Hamiltonian is just a free wave Hamiltonian. Therefore, the solution to this is just a free wave for each of the two particles, e to the I k1x1 plus e to the I k2x2. Or I could put k2, k1 the other way around. Okay? And now this matching condition gives me a condition for how these particular combinations are to be combined together. Okay? So these are just the discontinuity conditions. And now the wave function has to be a linear superposition of the two possible choices of distribution of quasi-momenta onto the particles. Why can it only be that? Because these are the only combinations that preserve energy and momentum, as has to be the case under this collision. Therefore, you write a general ansatz, a general form for the wave function, as this linear combination of these two choices of permutations of the quasi-momenta. And now you apply the boundary condition that you got, and that boundary condition gives you a relationship between the amplitudes of the two parts of the wave function. That's it. This condition you can write as an analytical form taking the shape of a phase. So the actual ratio of the amplitudes takes the form of some complex number over its conjugate. Therefore, it's unimodular. Therefore, it can be written as a phase. This phase, just this phi here, is then just an explicit function, and that's where you find the thing where, Felix Bloch walks out of the room because there's a logarithm you can write as an arctan, and he put all of this to 0. Well, at least for the spin chain, not for this one. But this scattering phase here depends on the rapidity. So I use the word rapidity as synonymous with momenta, quasi-momenta for the particles. So the two particles collide. They come into the collision with their own internal momenta. And the scattering phase that they obtain, so if you keep one of the particles fixed, the other particle comes with its momentum here, but then it hits and it has a shift. And then it keeps on going. But this shift, it depends on that particle's momentum and that particle's momentum and the interaction parameter. Okay? However, it is fully codified. So this gives us a complete solution to the two-particle problem, because the wave function now is this explicit linear combination of these two choices of distributions of the quasi-momenta onto the particles, related to each other by a fixed phase shift, solving the Schrödinger equation. Okay? Is that cool? And that's it. You know everything there is to know about beta ansatz, essentially, at this point, because all the rest is a straightforward generalization of this. Okay? If you have many particles, then the wave function is a simple generalization of this thing. First of all, you have all the possible places where particle positions coincide pairwise. Each represent a matching condition for different sectors of the wave function where quasi-momenta are distributed onto one particle or the other. Because of the delta function interaction. So you have in the n particle case, in the n particle case, the delta function interaction takes the form of, there would be a summation, for example, over all possible pairs of particles. Okay, and then I could do I could look at my Schrödinger equation with, say, x3 and x7 colliding onto each other and all the other x's somewhere else. And then I integrate over the relative coordinate x3 minus x7, and I'm only concerned by the one delta function here, x3 minus x7. And then this one here I can solve in exactly the same way as we did the two particle case. Okay?
So I should just enumerate them, like you say here that j plus 1 is equal to j.
That's right.
But like x7 is not...
Yeah, so here we are dealing with a bosonic wave function. Therefore, by declaration, the wave function is a totally symmetric function of all coordinates. And therefore, I can choose to codify my wave function fully in a domain in which all the coordinates are ordered. If I give you the wave function throughout this domain, you know the wave function everywhere because it's totally symmetric. Therefore, when I write the Schrödinger equation, I can do this strict ordering here, which means that when I solve the Schrödinger equation, I'm only concerned in collisions between successive coordinates because the others don't collide, or I get them by redundancy invoking symmetry. So then the problem reduces to this simpler reduced set of equations whose solution is completely general in that case. Cool? Okay. Other questions? Okay. So this is the beta ansatz. Okay, and once again, I flashed you the formula before in a slightly simpler form, but in spirit, that's all there is to it. What is the beta wave function? You have a certain state with a certain number of particles. You choose a certain number of quasi-momenta. And then you have to distribute these quasi-momenta onto your particles in all possible ways. Therefore, if n is your number of particles, you've got n factorial different terms in your wave function, each differing from each other by some permutation of which momentum you put on which particle, or alternately, which coordinate you associated to which momentum. Okay? Each of these different terms is characterized by a reordering of the positions. A reordering of two positions is enforced by the inclusion of a scattering phase shift between these particles. Scattering phase shift, which was this minus e to the I phi with the two coordinates. Okay? And that's it. So sum of free waves over all permutations, and then some term here that spits out for you precisely the scattering phase shift that you need to relate one term to the other. Okay? That's it. And now to actually prove that this really solves everything, there's a little bit of work, but once again, we're not going to do that here because you have all the material now to go reproduce these things step by step with these notes, and that's it. But what I want you to understand is that this treatment here is really universal to all of the kind of basic class of beta ansatz solvable models. Okay? The wave function that you have here is a sum over permutations. This beta ansatz, you could literally take this very equation, change the meaning of the symbols, and those would be the wave functions of a quantum spin chain like the Heisenberg model or the XXZ. Okay? It's the same thing. Okay, so that's the first bit. Okay. Now, once you have wave functions, again, as taught to us by many quantum mechanics books, what do we then need to do? We need to quantize the system because we have not specified what the allowed quasi-momenta are. And in order to be able to do counting, we put our system in a box. That's what we always do in quantum mechanics, because then putting a system in a box means that there's a discrete spacing between levels. So we can do a catalog and we can count. So we do the same. We do quantization of the wave function. Namely, we put now our Lieb-Liniger gas on a ring of circumference L, and we require periodicity. Here I could put an arbitrary phase. I could put arbitrary conditions that I would want. For simplicity, you just say the wave function is strictly periodic. If I take one coordinate and I shift it around the system, I will come back to the same wave function. This condition here on the wave function then translates onto a condition on the momenta. So if you had free particles, it would just mean that your momentum k would be integer units times 2 pi over L. That's it. The difference here is that when I take the particle around the system, it collides with the others. And therefore, my quantization condition is not e to the I k L is equal to 1, but it's e to the I k L is equal to all the phases I've picked up when I've bumped into all the others. And all these other phases depend on the momenta of the other particles. Okay? So here are the beta equations, namely the quantization conditions for quasi-momenta in a beta-ansatz solvable model. These are now purely algebraic, those transcendental equations for the set of rapidities inside your state. Here for 2 particles, the same holds, of course, for n particles. If I look at the n particle case, it's a simple generalization where now I collide with all the n-1 other particles. And here again, we rewrite this as just this meromorphic function of the rapidities. These equations here, if solved, provide a fully explicit solution to the Schrödinger equation. So now, to construct the basis of eigenstates, I have to solve the mathematical problem of finding all solutions to these equations. And the theorem is that every single state maps one-to-one onto every single solution of these equations. So now the problem has become purely algebraic. Yeah, just unfortunately these equations are transcendental. You cannot solve them analytically. There's no way you will ever, anybody will ever solve those analytically. Okay? However, you can still do stuff with those. Okay, so that's the statement. So now, to construct a basis of states, that's what I do. I write beta equations. Here I've just taken the log. This is a more common form that you would have. So in the absence of interactions, you just have momentum is equal to 2 pi over L times integer. But now we've got an interaction term. I've got these equations. I sit down and I try to find all solutions to this. For each solution I find, I can substitute the solution into the beta ansatz, and I get my wave function. Or I can compute the energy and whatnot. Okay, so that's the way you construct a whole set of states for these models. Okay? Yeah. Yeah, so that's for the Lieb-Liniger model. Now, very briefly, you can also do exactly the same thing for the Heisenberg chain. Okay, so maybe we've already seen the Hamiltonian. Let me just see maybe I'll just jump even to the actual solution. So for the spin chain, you have to solve again the. Maybe actually I was good here. So for the spin chain, you have the same kind of problem here, except that you're on a lattice. You have to look at interactions between neighboring spins, but you can still do the same thing. The equations look dangerously similar. Namely, the wave function is a linear combination of plane waves whose relative amplitudes are given by some scattering phase. Okay, very similar looking things, just the details of what this function is and what the meaning of this k is are different. However, the meta-morphology of these equations is identical. So here is your beta ansatz for the spin chain. You get the quantization, you get the beta equations for the spin chain. And here, once again, in the general case, these are the equivalent spin chain equations for the wave function, so the beta ansatz, and the beta equations, the quantization condition. Okay, and we could do the same for xxz, we could do the same for other models. It would all look like that. Okay, so that's the game. And I will let you fill in the blanks of all these approaches and solutions for these things. Okay? How many of you had seen beta equations before? A good number, okay. It's pretty good. Yeah, you didn't need to lift your hand, to be honest. I mean, to understand beta equations, I think I wouldn't even claim that. Yeah, I can tell you a lot about them, but yeah, I mean, yeah, difficult. Okay, so that's the kind of part that I would call coordinate beta ansatz part. Okay, that would complete that. Now, one thing which I want to jump to is how we go to a system that has bigger and bigger size. Of course, we're interested in solving the 2-atom case, 3-atom case, and whatnot. But, like I said, there's an interest in understanding how large systems behave. Because, of course, when you put many, many particles together in the presence of interactions, you get complicated phases of matter. So that's what we'd like to do here. Now, what's going to occur is that we're going to tweak the language a little bit here. Because instead, so before in coordinate beta ansatz, I would give you a set of quantum numbers that you would feed into the beta equations. So these quantum numbers are really the integers that are occupied in the beta equations. And some integers are not occupied, so they're like holes, particles and holes. And I would give you those numbers. You would have this coupled set of equations in the thing, and you'd go about solving this coupled set of equations. Now, if you've got a large number of these things, it is better to go to a kind of continuum formulation where you say, I will give you a kind of smoothened version of the places where the quantum numbers are occupied and the quantum numbers are not occupied. So there's a density of occupation now. Right? And the beta equations now become a functional integral relationship for that density. So that's what you have here. So you take the discrete beta equations and then you take the limit of an infinite system and you define these continuum versions, namely the kind of density of occupation of these quantum numbers. And now you can write this thing, you can write the original beta equations as a functional relation. So now instead of labeling the eigenstates by sets of quantum numbers, we actually label the eigenstates by a function. Each function is then associated to a state. Okay, so again, maybe just accept it and read these things here to see how this is done. But now the beta equations become an integral relationship between the density of particles and the density of holes. And each solution I find of this equation gives me a stack of states in the thermodynamic limit. And now if I want, for example, to sum over all states, what I need to do is a functional integral over these occupation functions. Each occupation function labels a set of states. Okay? So the message for this whole like thermodynamic beta ansatz is that in the infinite size limit, I will enforce summation over states as a functional integral, integrating over all distributions of these quantum numbers here. Again, I invite you to really learn these things. I will not use that very, very much in the lectures, but sometimes when I talk about quenches, for example, I will present for you equations for these densities, and that's going to be based on these ideas here. But just accept that when you go to an infinite size limit, instead of specifying quantum numbers, you're essentially specifying for me a distribution of these quantum numbers, and that's the same label. Okay? And we'll make use of that. Okay, now in view of the time, what I'm going to do is at the beginning of next session, I'm going to give you a 10-minute crash course on the algebraic beta ansatz before we then start applying all these things. But the core ideas of today are, where do the beta ansatz wave functions come from? Solutions to the Schrödinger equation for two particles. How do they generalize to many particle systems? Trivially, by just essentially ensuring symmetry of the wave function and applying the same idea to all possible collisions in there. Once you go to the thermodynamic limit, so that's for to construct the wave function. Then quantization, state counting, comes from the beta equations, which are constraints on the quasi-momenta coming from enforcing periodicity of your wave functions in a finite size. And then when you go to an infinite system size, keeping this counting, instead of summing over discrete states, you are summing over distributions of these numbers. And that you would do with a functional integral, okay? So you'll see some equations that correspond to that. So I invite you to have a look at the, I mean, if you have your phone, if you have Signal or something, you can have a look at these things now or later. And hopefully you've got enough material at least to be able to take a plunge here. Okay? So I guess I should stop here. 1 minute 40. Thank you.